Okay, great. Thank you for inviting me to SDNS to talk about why secure decentralized namespaces are the future. So this is a shortened version of a talk I've given before. It's shortened and updated. I'm just going to blow through some of these slides as fast as I can while still being coherent so that there's room for Q&A at the end. So a little bit about me. I am a software developer with over 2 decades of experience writing software, mostly in information security related areas. And today I'm going to talk about a problem that has been discussed much during this conference, which is the problem of the man-in-the-middle attack on DNS, but also with a focus on HTTPS. So a brief overview of the problem. User enters a URL into a web browser. They enter a domain, so okTurtles.com or .org, and they hit enter. What happens is that DNS returns an IP address, and their web browser then connects to that IP address. We know that this process isn't secure. So that IP address returns a certificate, and that certificate is then verified using a completely different system, a different protocol called X509, also known as SSL or TLS. So every computer ships with a whole bunch of root certificate authorities. These are entities that are able to sign these certificates. And if one of those entities has signed the certificate, then the lock icon appears in the browser, and the user is told that the connection is secure. So there are several problems in this one problem. Let's quickly go over them. So the first problem we've already talked about. DNS has no security. The man-in-the-middle attack is trivial on DNS. User connects to a DNS server, and somewhere between the two of them, an attacker gives an altered response. So you expected 5.5.5, and you got instead 10.10.10.10. Problem number 2 is that HTTPS, which is an attempt to address this problem, is very weak. So in this case, the bad guy just gives a certificate that is invalid. So there are over 1,000 root and intermediate certificate authorities that are able to sign these certificates. And if any one of them is compromised, then the entire internet is compromised. Is a certificate is sent over to the computer. The computer asks if it's legitimate, and someone out of a crowd of people shouts, "Yeah, sure, believe me." And the browser then believes and shows the lock icon. So there are other problems within this problem, however, and that is that DNS and HTTPS share different. So what do I mean by a namespace? Well, a namespace is a space with a bunch of names in it. And more importantly is that this namespace attempts to maintain key value mappings between these names. So if you already have a name registered in this namespace defined in it, then attempting to do it again is a no-go. So that would be invalid if you're trying to override improperly one of these keys. So again, a namespace is just a mapping from names to arbitrary data. Now, the problem is that in both DNS and X509, neither one of these actually clearly defines a namespace. And not only that, but there's no overlap between the two systems, between DNS and X509. There's no consensus on what that mapping should be. So DNS and HTTPS share different namespaces. So for example, you can have apple.com version 1 or apple.com version 2. And this is a serious problem for websites and companies because they don't actually have control over their digital property, in this case, their name. So problem number 4 is that it's even worse than that because within DNS and HTTPS each have different namespaces. In DNS, there is no consensus over the namespace. So it is possible in DNS that that system returns different values for apple.com. And the same is true of HTTPS. That also can return different values for apple.com. So this one problem is really 4 problems. DNS has no security. HTTPS has weak security. DNS and HTTPS are different namespaces, and they each within themselves have different namespaces. These four problems have one solution, and that is to combine DNS and HTTPS into a single namespace using decentralized consensus. And there is some caveats to how to do this if you attempt to do it. There are right ways and wrong ways of going about that. So before we cover that, let's go over some of the past attempts at solving this problem. Those attempts include X509, DNSSEC, Convergence, HPKP. We've covered X509. DNSSEC is complicated. It has a whole bunch of RFCs that define it. It's difficult to deploy. It's unnecessary. And it's broken. So there's a website that keeps, or at least used to keep track of DNSSEC outages, and these are just some of them. This is a list from 2017. I'm sure the list is much longer by now. And that's not all of them, you know, it kind of goes on and on and on. It's less secure than X509 because there are different classes of entities that you have to trust. The registrars, TLDs, and ICANN, and if any one of those is compromised, the system kind of breaks. So convergence and perspectives are an improvement, but they also have their problems because they are ineffective against server-side man-in-the-middle attacks. And they also have additional problems. For example, they don't have instant startup. Can a new server use a new certificate immediately and be trusted by clients? No. And there are other additional issues. So users also in the system have to trust a hard-coded list of notaries that attempt to kind of build on a foundation of sand that doesn't actually work very well. And this is the issue with convergence and perspectives, is that they build on top of known existing broken systems like DNS that do not have an established agreement on what the actual namespace is. The improvement that they try to add is consensus. And consensus is when a group of independent entities agree on a decision. For example, if a key value mapping is valid, using some voting threshold. So then we have DNS script, which is nice, but it doesn't solve the problem either, as we know. It's mainly on the client side, and it doesn't protect against upstream man in the middle. It's also difficult to use. Pinning is a very strong method, but it's very brittle. So it's difficult to use, it's ineffective against man in the middle on the first visit, and it's broken for users with broken clocks. So new attempts include certificate transparency, key transparency, Connix, and DPKI. Here is on blog.okturtles.org, we compare all of these different systems in detail. You can read that blog post. But the short of it is that neither certificate transparency nor key transparency are able to prevent man-in-the-middle attacks. They might be able to detect them, nor are they censorship resistant. Connix improves on them and potentially offers man-in-the-middle prevention, not just detection, but it also is not censorship resistant. DPKI possibly checks all of these boxes, including internet scalable. Most likely, we should be able to get that. So we'll get into DPKI, and that is combining the DNS and HTTPS into, well, not a single namespace, but actually multiple namespaces. So each one of these TLDs would be connecting to a different decentralized consensus-based namespace. That is the idea. And this is required. This is a requirement of DPKI. And DPKI says you cannot have a single decentralized consensus-based namespace powering the internet. Now, why is that? Before we get into that, let's ask why blockchains? Well, that's because they offer decentralization for powering the namespace. They're decentralized namespaces. And the advantage of decentralized namespaces is that they offer censorship resistance. They offer actual ownership of the domain to the people who have registered them. And that remains true as long as they remain decentralized, as long as there is no consensus capture. So why multiple blockchains? Well, that has to do with that consensus capture thing. There are a few sort of stipulations. One of them is called Zuko's Triangle, and that says that any namespace can have 2 of 3 properties. It can be secure, global, readable, secure, human readable, and global, but not all 3. 2 of those properties, not all 3. And there's a similar triangle that is very blockchain specific called the DCS Triangle, which says that any blockchain or decentralized consensus system can be decentralized and it can have consensus, but then in that case, it cannot scale. So The DCS theorem shows a proof of this triangle. If you do a search for it, you'll find the paper and you can read about that. This is very important because it says that if you attempt to achieve internet scale, you're going to lose one of these properties. You'll either break consensus or you'll break the decentralization and end up with a centralized system. So what do? You cannot have a single blockchain is what this is telling us. So DPKI is different. It has to be different because it relies on consensus and recognizes consensus capture. Consensus is when there's agreement on what the actual namespace is, and consensus capture is what happens when you have a consensus system, in this case a group of people coming to agreement, or a group of machines, whatever the case may be, a group of entities coming to agreement. And in this case, the people that are using the system are only those people, but as soon as they start getting users, not all of those users can be consensus participants. You can read the DCS theorem to see why. And the more users the system gets, the smaller the consensus participants are, as opposed to when it comes to representing the entire user base. And this leads to centralization. So DPKI does not actually specify what kind of consensus protocol you have to use. It's a protocol for consensus protocols. And DPKI in two parts, basically the simplest part of it just says that you need to have TLDs that map to different decentralized consensus protocols. So for example, .eth would map to the Ethereum namespace, and .bit would map to Namecoin. There are various trust assumptions at these steps when you try to do the lookup. I'm going to skip these for time's sake. And DPKI also offers suggestions on how to do the lifecycle management of all of the keys that are involved in managing the registration of these names, so that, if you have a very secure system, it's a double-edged sword. You don't want to end up in a situation where strong ownership means that you've suddenly lost control of your domain because you flushed your toilet, down a river or a toilet or whatever the case may be. So getting around the DCS triangle, we do that avoiding this situation where you have a single system that gets more and more users. It starts out decentralized, then becomes centralized. And instead, you're dealing with a system that it has multiple decentralized consensus systems that are independent of one another. And that's good. So some potentially DPKI-friendly systems and protocols include decentralized identifiers, which is part of rebooting Web of Trust, the Ethereum name system, the Ethereum name service, Handshake, which is coming up in the next talk, Blockstack, which is Bitcoin-based. The Almanet group is working on some things related to this. Check them out. They're pretty cool. And the Brave web browser is potentially open to these kinds of protocols. So they might be able to lead in this area and support different namespaces. So what's next for DPKI? What's needed for DPKI? Well, we need people from different blockchains. So for example, from the Ethereum crowd and from the Handshake crowd to kind of get together and agree on what TLDs they're going to take ownership of and do resolving for in these browsers. And then some web browser actually needs to be chosen to support resolving these domains. So with that, I'm going to go ahead and take questions.